Hello, in this video, we will introduce measuring algorithm efficiency using big O notation. The big O notation obtains a function for measuring algorithm time complexity based on the input size. To simplify the notation, you can ignore multiplicative constants and non-dominating terms in the function. Consider linear search. The linear search algorithm compares the key with the elements in the array sequentially until the key is found or the array is exhausted. If the key is not in the array, it requires n comparisons for an array of size n. If the key is in the array, it requires n divided by 2 comparisons on average. The algorithm's execution time is proportional to the size of the array. If you double the size of the array, you will expect the number of comparisons to double. The algorithm grows at a linear rate. The growth rate has an order of the magnitude of n. Computer scientists use the big O notation to represent the order of magnitude. Using this notation, the complexity of the linear search algorithm is order of n. The time complexity is also known as running time. It is the amount of time taken by the algorithm to run measured using the big O notation. For the same input size, an algorithm's execution time may vary depending on the input. An input that results in the shortest execution time is called the best case input. And an input that results in the longest execution time is the worst case input. Best and worst case analysis are to analyze the algorithms for their best and worst case input. Best and worst case analysis are not representative, but worst case analysis is very helpful. You can be assured that the algorithm will never be slower than the worst case. An average case analysis attempts to determine the average amount of time among all possible inputs of the same size. Average case analysis is ideal, but difficult to obtain because for many problems, it is hard to determine the relative probabilities and distributions of various input instances. Worst case analysis is easier to perform. So the analysis is generally conducted for the worst case. The linear search algorithm requires n comparisons in the worst case and n divided by 2 time comparisons in the average case if you are nearly always looking for something known to be in the list. Using the big O notation, both cases require order of n time. The multiplicative constant, 1 divided by 2, can be omitted. Algorithm analysis is focused on growth rate. The multiplicative constants have no impact on growth rates. The growth rate for n divided by 2 or 100 times n is the same as for n. So let's look at this table. You'll see the reason. For this table here, we have this n is size of 100 and 200. This is the function fn. So fn is n divided by 2 100 times n. So you look at those numbers here. If you have this, using this f200 divided by f100, so this is all 2. So the growth rate is the same, regardless what constants you have for this function. So the constants can be ignored. Also, the dominating part you can keep, but the non-dominating part should be omitted to simplify the notation. So let's look at this, another example. Consider the algorithm for finding the maximum number in an array of n elements. To find the maximum number, if n is 2, it takes 1 comparison. If n is 3, you need 2 comparisons. In general, it takes n minus 1 comparisons to find the maximum number in a list of n elements. Algorithm analysis is for large input size. If the input size is small, there's no significance in estimating an algorithm's efficiency. As n grows, the n part in the expression n minus 1 dominates the complexity. The big O notation allows you to ignore the non-dominating part. Here is -1 in the expression n minus 1, and highlight the important part. So that's the here in this case is n. Therefore, the complexity of this algorithm is order of n. The non-dominating part -1 is omitted. The big O notation estimates the execution time of an algorithm in relation to the input size. If the time is not related to the input size, the algorithm is said to take constant time with the notation order of 1. For instance, a function that retrieves an element at a given index in an array takes constant time because the time does not grow as the size of the array increases. We're going to use this summation a lot in the upcoming videos to analyze the time complexity. So this is the summation, the sequence of numbers 1 plus 2 and all the way plus n minus 1. So that is here. It is this n times n minus 1 divided by 2, which is order of n squared. And so this, if you have 1 plus 2 all the way plus n, it's the same thing. It's order of n squared. And this is the as 1, as 0, as 2, as 3, all the way here as n. So that is order of as n. For 2, that's order of 2's n. That is all for this video. See you on the next video.